Okay, hello everyone, and welcome once again to the Convex stream. Hope you're all doing great. So today's topic is an interesting one, and it came out of some of the conversations that we had on the Discord. But people are interested in the idea of what is the internet computer? What is an internet computer? And what can you do with it, and how does that relate to what we're doing with Convex, and how does it relate to sort of the future of sort of decentralized technology? So super interesting topic, and I think it's a chance to talk about some of the sort of big ideas that are relevant in the in the decentralized space. So good topic to choose. As always, we'll be live on chat. So if anyone wants to yep, not seeing the chat. I'm not sure if this is working. 1 second. Let me just double check. Hey there. Sorry. Yeah. So OBS was playing up a bit there. Not quite sure what happened, but I just see the chat now. See you guys. See you guys are there. So that's good to see. So yeah, sorry about the slight technical glitch there. So yeah, so we'll talk a bit about the internet computer. As always, if you've got questions, then just fire them in on the on the chat, and we can have a conversation about any of the sort of the topics relevant to this that people are interested in. So um, let me share a couple of thoughts that certainly I have on this topic. So if we think about what is the internet and what is a computer, and therefore what is an internet computer. So I think one of the most important things is that the internet was always designed, first and foremost as a global communication network. It's a way of sending messages, sending information between different participants in a system. And one of the reasons the internet is so powerful is that it is actually quite simple. Yeah, it's just streams of bytes being sent from one computer to another, a host in internet terminology, or a client on the internet. And the network itself doesn't really have much logic in it. It's just pipes. Yeah, it's sending, from a logical level, it's sending information from one machine to another, and that's being used to achieve all the wonderful things we see on the World Wide Web, and with decentralized applications and all the different systems that exist on the internet. Um, Obviously, the internet does have some information that is important, let's say, to the operation of the internet, which is stored. So things like DNS records, and obviously a lot of things like caching happen in some of the routers. But by and large, it's just for sending data from one place to another. And the internet doesn't really say much about what those nodes at the edge, um, how they interpret that data and what they do with it. So, of course, the classic model of having a web server, for example, is just a system connected to the internet that clients connect to, and they send HTTP requests, and the web server comes back with some HTTP document, which then the browser can display and provide all the different World Wide Web experience and browser functionality that the user wants to see. So the internet itself is just acting as a communication channel between the client and the server. And actually, that's really powerful, because it means that the infrastructure doesn't need to know about what protocol, what the format or the type of information that's going over it. It just makes sure that the messages get from one place to the other in a reliable way. And that's what makes the internet so powerful. No one had to change the internet to create a new protocol, because you can use the existing communication things on the internet. And of course, that means that over time, people got more and more sophisticated, being more and more powerful systems, and we ended up with obviously the large centralized platforms and systems that we see today. Your Googles, your YouTubes, etc. And of course, those systems are centralized. They're under the control of one organization, but they're sitting in data centers in various places around the world. And at the sort of the very core, they're still just ports open on the internet that clients can connect to, send requests, and get responses back. So I always see the internet as fundamentally a communication network. It's a way of getting information from one place to another. And if you want to implement something meaningful, you're going to need two things which I think are fundamental to computation. You're going to need data, and you're going to need compute. So data is whatever data your application is going to use, whether it's in a database, whether it's on a file system, whether it's in your server's main memory, etc., etc. All the data that makes the application or the system operate. And you need computation, which is fundamentally transforming data from one form into another. And really, at its heart, that's all computers do. They've got some data, and they've got some way of receiving data, some kind of input, and receiving messages. They've got some way of computing and transforming the data, and they've got some way of performing output, so that the results go back or to whoever wants them, or it performs some action, or it controls a robot, whatever kind of output you want your system to achieve. So it's data and compute are the fundamentals of everything we do, and that's sufficient for any computer that exists. I mean, they all effectively operate that way. And I think what's interesting about the internet, of course, is the internet in itself doesn't have data, or at least it doesn't have general purpose data. As I say, it has some very specific data that relates to the operation of the internet, like DNS tables, etc. But it doesn't store data itself. You rely on all of the hosts, the servers on the internet to store data. And it also doesn't have compute. It's not really doing any complicated logic. It's just sending the bytes unchanged from point A to point B. So the internet, although it connects computers, it doesn't really operate as a computer. A computer needs, as I say, input, output, data, some kind of storage, and some kind of compute to be a useful general purpose computer. So I've always thought about the idea of the internet computer as, how do we give the internet the same kind of capabilities that a computer has? So specifically, we want the network itself to be capable of storage, of managing data, and we want the network itself to be capable of doing compute. And the input and output of an internet computer, well, it's either messages to the internet computer, or it's messages, information flowing out of the internet computer to various different destinations. So it's almost like taking the computational capabilities that used to sit in servers and in clients and saying, okay, actually we want the network to be able to do some of this. And you might ask, well, why is that important? Why do we need that? We've already got perfectly good servers, perfectly good clients, and various different systems connected to the internet that can do all that. And I think the answer here comes back to decentralization. If you want a model where you can do compute and storage in a truly decentralized way, then it's never going to be adequate to rely on a single centralized system or set of servers that are authoritative in that data and in that compute, but are under the control of a single organization. That's a centralized system. So to me, the internet computer is about bringing computer capabilities to the internet in a way that's decentralized, so that there's no single entity controls that. So, I mean, what are the properties we'd like to see in an internet computer? Well, I mean, first of all, it should be obviously global. It should be internet scale. It should be able to manage, the kind of demands of a global system. It should be open, so people have got to be able to access it. if you're doing something purely for yourself or with a small set of trusted partners, then there's not really much need for a decentralized system. It might be more efficient, maybe in some cases, but typically decentralized systems have their own costs. So you might as well use a centralized system if you're just keeping your own data and managing the data of a small number of trusted partners. So it's really, if you want to build something open and public, where anyone can participate, that you might want an internet computer to be the sort of foundations of some of your systems. I think there's also a question about reliability and unstoppability. Yeah, can it be relied upon to execute faithfully? And can you validate that? Can you confirm that it has in fact executed faithfully? And that becomes particularly important if you're going to use this internet computer to mediate economic transactions or enforce smart contracts. And I guess this is where the sort of intersection happens with Convex. We're building Convex as an engine for open economic systems, and that's precisely what we want. We want a virtual computer at internet scale, which can faithfully and reliably execute economic transactions that all users can participate in and have equal access to, and that is going to be unstoppable in the sense that no single entity can censor or prevent that system from carrying out its purpose and carrying out the legitimate requests of users, which is what ultimately any computer is meant to do. It's got to provide value to its users and to the systems that it interacts with. So maybe a bit long-winded, but hopefully that's given an idea of how I think about the internet computer and why I would describe Convex as an example of an internet computer, because it is decentralized, it does have full compute capabilities, it's got full storage capabilities, it can execute programs in a sort of censorship resistant, unstoppable way, it can enforce smart contracts, it can mediate value exchange, all of the different properties that we want to have in terms of building open economic systems. Now, I don't think that's the only purpose of an internet computer. I mean, certainly that's what we're enabling with Convex. But you could easily see an internet computer be used for other purposes. Yeah, you could use it for some kind of public service. Yeah, so like voting, citizen voting or something like that. You could use it for authenticity checks. Yeah, sort of some kind of global public notary. These kind of things. So there's many different applications that make sense on an internet computer. Some of which are also a good fit for Convex. Although of course Convex is primarily focused on how do you create economic systems of value exchange. Question: will an internet computer be permissionless? That's a really good question. So I think that's a design decision. It's a design decision in that you can absolutely make an internet computer that's entirely permissioned and entirely restrict. And let's say, what do we mean by permissionless? Permissionless means that you can participate without having to get someone else to authorize you to say yes, you can do that. Let's say if only 10 different people were able to transact on a particular internet computer, and it would only accept requests from them, then you would say that's a permission system. And maybe the permission's variable. Maybe there's a way that you can add additional participants who have permissions. But you certainly could build a fully permissioned internet computer. It's also a question about what permissions you're talking about. So, for example, I don't think any crypto network is totally permissionless in the sense that in order to do certain things, you generally have to prove something. Yeah, you generally have to have a signature, and anyone can't do anything. There are restrictions to what you can do and what you can't do. So, obviously transferring funds, for example, you should only be able to transfer the funds if you actually own those funds. Is like a sort of fundamental position on any sort of economic system. But it's permissionless in the sense that a system could be permissionless in the sense that anyone is allowed to transfer funds that they own. Yeah, and anyone is allowed to interact with the system. Anyone is allowed to make use of the system. Anyone maybe is allowed to query the system. Yeah, if you're not actually moving any funds, if you're not actually executing any transaction, then anyone has open public access to it, which is more in spirit of a typical crypto network is sort of relatively permissionless. And I think there's also a distinction between, is it permissionless for users, like any user can use the system, or is it permissionless for, let's say, network operations, like peers or nodes on the network? Do you need permission to operate a peer? So some systems could be relatively permissionless for users, but very strongly permissioned. Maybe there's like only 20 organizations allowed to run a peer on the network. So then that is, it's permissionless in one sense, but also some aspects of the network are still sort of quite heavily permissioned. So these are all design questions. Yeah, does it suit your use case? Does it help solve the problems that users need to solve? And does that provide the right kind of infrastructure that that particular application needs? So will it be permissioned or permissionless? I mean, that's design choice, I'd say. And I think that brings us on to a very good point that I think there will be many internet computers. In fact, there already are multiple internet computers of various different kinds. And I would describe an internet computer as a full computer, so capable of Turing complete operations, capable of storage, capable of compute, and running in a decentralized model. I think that would be my three criteria to define an internet computer. And by that standard, there are already many internet computers. And indeed, if you were to boot up two different convex networks, you would have two computers. Yeah, they'd be two different convex computers, but that's a perfectly valid way of these systems existing. And then, of course, then we get on to questions about, well, what is a bridge? Well, a bridge in this context is really just a link between two internet computers. Yeah, a way of sending a reliably, hopefully reliably communicated transaction between two different computers that somehow need to sync up. And it's the same with regular computers. Yeah, if two computers get out of sync and you've got the files are like this on one of them and the files like this on the other, then you need to pass some messages between if you want to reconcile the differences and sort of work out the changes that need to be made to bring them back into sync. And of course, that's what convergent proof of stake is all about. The CPOS algorithm is all about how do you keep a whole bunch of peers in sync with regard to consensus. Another question. Setting a minimum stake for a peer does create a barrier for permissionless participation. Yeah, so that's a good point. So and we haven't. We will be testing this in Protonet, but probably the minimum stake to run a peer that we'll run with is 1,000 Convex Go coins for a minimum for a peer to be considered a fully participating peer on the network. So it's permissionless in that anyone can run one, but yes, there are rules that you have to follow. So the protocol on which an internet computer runs defines the rules by which participation has to happen. Yeah, and for a peer we set a minimum because there's not much point having a whole bunch of low stake peers. We want to make sure that it's that the peers are properly supported, properly maintained, and that they're going to be useful contributors to the network. That's why we put a minimum stake on it. But we will review that in Protonet. Yeah, that's one of the reasons we have the Protonet phase is to say, well, look, have we set these protocol? This is really a protocol parameter. Yeah, is that the right minimum stake? Does it provide enough ease for people to participate, but also, you want to stop things like spam. You want to stop things like, people just, messing around and, creating a bunch of meaningless peers or spamming things at people. It just doesn't help anyone. So we want to make sure we get the balance right between, what level of permissionless makes sense. So yeah, good point. Yeah, if you've got a system of delegating stake like Convex does, then you don't need to have any. There's no minimum on delegated stake. But of course, delegated stake has to be linked to a particular peer that you want to stake on. So it doesn't allow delegated stake allows you to get a share of some of the peer rewards, but it doesn't let you actually operate a peer. Yeah, so it's the operation of a peer that we put the minimum stake on. But yeah, great question. And this is about, as we talk about internet computers, you've got to really think very hard about these design decisions, because this is what will make the difference between a efficient, scalable network that has reliable uptime and everyone can rely on and everyone can build meaningful economic systems on top of, versus something which is going to fall over when something goes wrong, or in some unexpected scenario, or when even someone maliciously decides they want to attack the network. So a lot of the Protonet phase is going to be just making sure that we've got all these things right, and that we can't take down the network, and that it does have the right incentives for participation in positive ways. So yeah, some more questions from the chat. Presumably a company or academia could set up a private internet computer. Yeah, absolutely. So no restriction really to anyone building these things. I think the question should always be, do you really need one? Yeah. So companies are often quite happy with a centralized solution, and that's because centralized solutions are pretty mature. Yeah, they are very well developed technology. They're good at what they do. They designed to meet company needs and organizations' needs, and companies usually want control. Yeah, they want to be able to control their email. They want to be able to control their databases. So for them, there's maybe not so much value proposition in having an internet computer that everyone can interact with, because that's not what they want it for. Yeah, it doesn't really fit the use case. So I say you can, but maybe you should think about if you should. Yeah, because I'd certainly never say you always pick one technology for every single use case. That would be unwise. Yeah, because some things are better suited for other things. And for private companies, a centralized solution may be perfectly okay. They might. A lot of the time they might say, okay, well, we've got a lot of subsidiaries, we've got a lot of international trading, we have a lot of partners, we actually do want an internet computer as the foundation of some of our systems. So that's also a valid choice, but you probably need to be maybe a bit larger, a bit more decentralized, and maybe wanting to do economic transactions on your system. Then it might make more sense to have a private internet computer. But yeah, very, very good question. I mean, I think we will see that. I think we'll absolutely see that. And it will become more common that people have private internet computers that maybe are operated by third parties. Because the nice thing about an internet computer is, well, they're designed for decentralized operation. So you can have a whole bunch of third parties around the world operating the nodes. You don't have to run that infrastructure. You can rely on some decentralized network to do it. You just provide the right incentives so that they operate that network according to your preferences, and you're good. That's a perfectly valid system. And actually, one of the things that I really want to get in Convex 2, so it probably won't be a thing for Convex version 1, but for Convex version 2, I think what we would like to get is something like a sort of child network model. So you can have different child networks that then connect back up to the main network. And one of the reasons for that is so that people can have their own private internet computer that maybe they're using for a specific purpose. Example might be a computer game. Yeah, they might want their own version of Convex for running their own little ecosystem that can still link back up to the main network, but 99% of the time it's running a little mini ecosystem of its own that doesn't need to be connected to the broader space, and it doesn't need to be in the same consensus set. And you might as well have a sort of separated child network, or a semi-separated child network. And I think it becomes very powerful if you can say, okay, well, we've got a way of automatically coordinating these things, but without actually putting too many restrictions on the children. So the children can do things in different ways. They can have maybe different economics. They can maybe have different permission levels of permissions. They might have even different rules on privacy or this kind of thing. So that's definitely something we'd like to be able to support in the future, and that will be great for organizations, companies that want to just spin up these things for specific purposes. So yeah, great point. So yeah, we will probably see in the future. Will it be it's kind of like cloud, yeah. So it used to be that everyone would manage all of their databases on premise. You'd have a database server in a room, storing all of your corporate details. People would you'd have a private corporate network. You'd manage the servers. You'd have system administrators, etc., etc. And as the cloud technology developed, people realised actually for many use cases it makes sense for us not to have a server room. Yeah, we're just going to pay hosting providers to run this in a virtual manner, sort of a cloud service. Don't ever need to know about the infrastructure, what it is, where it's located, and a lot of workload, particularly for small businesses that got really no reason to run a data center. All of this stuff moves to the cloud, and I think what we'll see in the future is a significant amount of workload. Probably not all of it, but certainly some of it will move to internet computers, which is like sort of the next evolution of the cloud. Some workloads will make a lot more sense on a global internet computer than they would on a privately managed centralized cloud solution. So that will be very interesting to see, I think. And I think the challenge is obviously cost and efficiency is currently far more favourable for centralized solutions. Yeah, so hopefully Convex is changing that, but you've got a lot more power in a standard centralized server than you would have on your typical internet computer, and that's because there's extra overheads. Yeah, there's all the consensus, there's communication, there's the cost of running things and validating things, and making sure it's cryptographically secure. All adds up on costs, and you have to pay multiple validators. You have to incentivize many people to run nodes. So rather than just having one or two computers with servers with backups and things like that in a centralized model, so you end up having to run more infrastructure for each system. So there's always going to be some cases where just for that reason you're going to want to run a centralized system. And that's fine, yeah. I mean, some workloads will suit it, some won't. But I think particularly when it comes to economic transactions, when it comes to contracts, enforcement of deals, transfers of assets with multiple parties involved, or interacting with markets, then internet computers make much more sense, because you want those things to be verified. You want them to be unstoppable in the sense that no centralized party can run away with all the assets, etc., etc. So for these kind of use cases, it makes a lot of sense to go to a sort of internet computer kind of model. So Okay, so we've talked a bit about, I guess, the theory of you know what is a internet computer. I thought it was worth just spending a bit of time on, and this was again something that got requested in the Discord, is talk about transactions. What does it mean to do a transaction? What does it mean to communicate with an internet computer, and to get something done? And how do those interactions look like? And of course, this is very, very important. If you're going to align these things to manage economic value exchange, you want to make sure that everything happens properly and it's well understood, and you know the risks, and all of these challenges. What I'll do is I'll outline the sort of general principles, and then get a bit more convex specific, and sort of make it a bit of an example. So your internet computer, it's fundamentally got input, output, data, and compute. So in general, what's going to happen is you're going to have some kind of transaction, some kind of message to the computer to do something on your behalf. So I think of it like pressing a submit button on a website where you're going to post some information to make a request to a web server. You have a transaction where you're making a request to the internet computer. The internet computer receives that transaction. It then applies logic to that transaction to say, hey, is it a good transaction? Because remember, we're talking about a decentralized network. You don't trust anyone. You're going to somehow validate that transaction is legitimate. If that transaction is legitimate, then you want to execute it. So you're going to run some code. That code may store some data, it may retrieve some data, it may transform some data, it may perform some computations, it may update some ledgers, balances of digital assets, whatever it is that you want this to do. It's just running a program, or running a function that is doing some compute, just like any function call in a regular programming language. You're going to trigger some operations. Some of those operations will change the data, will change the state. Once that is done, you will have a new state, so the data will have changed somehow, or presumably it's changed. If you send a transaction, you probably want something to change. There'll be some kind of new state, and then there will also be an output, and the output typically would be a result that goes back to the user to say, what happened, what was the result of the transaction? Did it succeed? Did it fail? Did it half succeed? Whatever the status is. So the user that's interacting with the system gets feedback and knows what they should do next. If something went wrong, they might need to do some corrective action or something like that. Doesn't have to be the only output going back to the user. There can be other outputs. You might be pushing messages to other systems. So you might have a system that pushes messages to another computer system, some kind of bridge. Something like Chainlink, where you've got a decentralized network which is sending messages from one decentralized network to another decentralized network. That would be another example of an output. Or you could have outputs that maybe get stored locally by nodes, so that they want to index. So a good example is logging, so event logs, this kind of thing, would be output that would be available to nodes or peers on the network. They see, okay, here's the outputs of different events, and those events might then get indexed, might get put on a sort of a block explorer kind of application where you can view all the events, you can see what happened, you can do audits, you can do analytics, all of these kind of things. So that will be another example of an output. So that's the sort of general cycle of a transaction. You've got some kind of message transaction going in, you've got some compute, you've got some change to the state, and you've got some outputs. Good question. Great question. So when new state, are we talking for individual peers, or the whole network now knows the new state? That is a really, really deep question. And it does depend on the network, and it depends on the consensus model, and it depends on the protocol. So Convex has a global state model. Yeah, so the global state model means that when the state gets updated, everyone gets the same updated state. Yeah, so in Convex, when a transaction is confirmed in consensus and executed and the state changes, every peer on the network knows and can confirm if they want. They can confirm with each other, they can cross-check, confirm the new global state. And that new global state then goes forward until the next transaction makes some change. So you can think about the Convex global state as being a state that sort of hops from the state before a transaction to the state after the transaction, and whatever happens between those two is the result of the transaction. That's sort of what Convex is doing. It's computing new global states. Now, if you had a sharded network, then you would have multiple different states, maybe by subsets of the network will be managing those different states, and then only those subset might know the new state. Yeah, and one of the advantages of a global state is you are not in danger of being out of sync. Yeah, you know that everyone agrees the new state, and everyone agrees what happened to asset balances and stuff like that. Whereas if you've got different subnets or different subsystems, you've got to solve the problem of how do you reconcile those if something's going between them. Yeah, and that's a hard problem. Reconciling data is one of the most difficult problems in computer science. So we short circuit a lot of those problems by having a single global state. It makes it much easier to build good, reliable solutions that are secure if you absolutely know that everyone shares the same global state. It's pros and cons as always. Yeah, I mean it does mean that we have to do a lot of work to make sure that all these peers simultaneously see the same global state and that they compute it in exactly the same way and that they can all confirm it, etc., etc. But it's worth doing, I think, because of the advantages of having a global state model. But you could have systems where literally there's very little global state. Yeah, you could have some networks can have pretty much the states on your phone. Yeah, and you might be the only person with certain bits of the global state. Yeah, until it's resynced. But then you obviously get synchronization problems. You have to solve a whole bunch of other different issues in those cases. But great question, yeah. So Convex global state model, and all the peers would know the new global state. So the whole network effectively knows the new global state. In other networks, it may be a bit different, and that adds complications in many cases. In that, on Convex, can a transaction between state be a block with multiple transactions? Great question. So logically, I think about each transaction changing the state from A to B, and then from B to C, and then from C to D, etc., etc. Logically, that's kind of what happens. In practice, many transactions get confirmed simultaneously in consensus. Yeah, so what might happen is 1,000 transactions get confirmed simultaneously at exactly the same instant as the network confirms consensus, because Convex confirms many transactions simultaneously as part of the design. So you can imagine it as you got 1,000 transactions confirmed. You could imagine it as each single state change from each single transaction, or you could imagine it as the state jumping from the start of that 1,000 transaction to the end of that 1,000 transactions, and you get the same result. You get to the same place. So you can think about it one way or the other, whichever way is easiest. So you could imagine the state jumping as the result of a block of transactions, and that's totally fine, perfectly good logical model. Just remember that is the same as a lot of small individual state transitions that happen over that time. And of course, this is where it's very important that the consensus confirms the ordering first, so that you know which transaction happened first, so you don't get double spend problems and these kind of things. Let me just share a quick slide just to try and explain a little bit more about what happens in Convex. Let me just switch up this. This is actually the transaction lifecycle on Convex. So there's like sort of six phases, if you like. So first of all, the user creates a transaction. What is it that they want to do? They've got some purpose. They've got some value exchange they want to execute, and they're going to create a transaction with some instruction to the network or to your internet computer. So let's say you want to send 1,000 Convex coppers to account number 16778. There's a command to do that, which is just a transfer command that's going to send those coins. That's what the user intends. Yeah, that's what they want to happen. Now, in order for that to happen, the user needs to prove that actually it's them who wants that to happen. So they need to do a digital signature. So they're going to sign this transaction with their private key, and that's going to result in a signature which gets sort of added to the message. So when you send the transaction, you're going to send it including, you're actually sending a signed transaction. Yeah, so it's the transaction itself plus the signature that proves that you authorized that transaction. So then that needs to get to the network. So the user then submits that transaction to a peer of their choice. So they send their signed transaction over to the peer. Peer looks at the transaction. They say, okay, is that a valid transaction? Is that a good transaction, or is that complete garbage? If it's garbage, or if it's, you know, if it looks invalid or anything wrong with the transaction, it gets rejected. But let's assume that it's valid. It's going to accept that transaction, and it's going to incorporate it into the peer's data structure called a belief. Now, belief is the way that convergent proof of stake synchronizes and achieves consensus. And that's going to have in it, it's going to have some data that represents the transaction. So in this case, our transfer transaction. And it's also going to have a hash. So that hash is the hash of the signed transaction, which can be used to identify the transaction uniquely. Yeah. So every single transaction is going to get a unique transaction hash, which is important if you want to go back and audit and see what transactions happened. So then we get the consensus phase, where all peers are going to be sharing beliefs with each other, and convergent proof of stake means that they converge to consensus, and that transaction then gets confirmed in the consensus. And that transaction is going to get confirmed at a particular position. Yeah. So if you imagine a whole bunch of chunks of blocks of transactions, there's going to be some transaction index, and there's going to be some position of that transaction in the block that got confirmed in consensus. So in this case, 67,868 is the block number, and the transaction is at index 45 within that block. That's useful if you want to audit and go back and see exactly when did that transaction happen, which order did all of these state updates happen. You can go back and look up that different position. So once the transaction is confirmed in consensus, so we finalized the ordering of the transaction, each peer is then going to execute that transaction in the order of the transactions that have been confirmed. At this point, it does a check of the signature. If the signature is invalid, the transaction still made it into consensus, but it's not going to achieve anything. It's going to get rejected during the execution because it's an invalid signature. So it won't do a transfer if the signature is wrong. But assuming the signature is correct, then it says, okay, you are in fact authorized to make this transfer, and it's going to update the global state. It's going to say the balance of this account has gone down by 1,000 and the balance of this other account has gone up by 1,000. So it does the global state update that represents the user's request. And then at the end of all of this, the peer has now validated the signature, it's executed a transaction, it's updated the global state. It then just returns a result to the user, which is a small record that has some sort of information about what happened. Most importantly, if you did a computation that returns a result, it will tell you what that result is. So transactions in Convex can return results. That's different from some systems. You can't return a result from a transaction. Convex does actually have a result, so any transaction can return whatever it likes as a result, and that goes back to the user. There's a message ID that doesn't really matter very much. It's mostly just so that the client knows, okay, this was the message I sent was this, and the message I got back was this, etc. So you can tell which send and which receive correspond to each other. And then it has some info fields, so it gives stuff like, where was the location of that transaction in consensus, and it a few other fields in there, like what fees got consumed. So various info about the result of the transaction gets returned, and that's basically the transaction lifecycle. So you go through this lifecycle every time a transaction happens. User is completely in control of the creation and signature of the transaction, and make sure it gets submitted to one peer. Once the user's done that, their job is effectively done. It's going into consensus. It's going to get into consensus. It's going to get executed, and the result comes back to the user at the end. The user doesn't have to do anything with the result. They can completely ignore it if they want. The transaction still happened. So question about this: submission and consensus, gossiping to network steps are basically instantaneous. Yeah, basically. I mean, so once the peers got the transaction incorporated into belief, they basically send it immediately out to the network. Very small delay. A few messages need to pass back and forth to reach consensus, so there is a bit of lag on that based on your internet connections. Primarily that depends on the speed of the internet connections between the peers. Yeah, so if the peers have fast internet connections, low latency connections, then the messages get back and forth faster. And then after a few hops of those messages, then the peers will have confirmed consensus. Then each peer executes the transaction and returns the result. Again, that's effectively instantaneous once the transaction's confirmed. Let me just, I might as well just show it. Let's say I launch a quick test net here. So we've got a little mini convex test net going with 3 peers. If I jump into this one, I've got it like a REPL. So now this is my window into the internet computer. Yeah, I'm seeing a terminal, if you like, into the internet computer for my account number 12. That's the account I'm executing with at the moment. Anything I put into here is going to get executed as a transaction and return a result. So that is following that full result lifecycle that I just outlined. And as you can see, in this case, the results are, pretty instantaneous. It's coming back with the result of these little mathematical operations very quickly. And as it's a computer, yeah? General purpose computer. You can do mathematics, you can define functions, you can write some code. There you are. So here's a fun program. So I can string hello and name. Okay, so I define a function. So this is just programming, yeah? So I can go foo Bob, and it says hello Bob. Yeah, it's a computer. You can program it. And obviously you can program it to do things with all the digital assets and all of the economic systems and stuff. But at its heart, it's just a computer. It's a machine, and everyone has their own account on the machine. Everyone's account is protected from other people's accounts, so you need the correct digital signature to run things in your account. So in that sense, it's like one of the old mainframes where you could have multi-user systems where everyone could have their own little account they log into, and have their own setup, etc. Now there's some tools in this. So one of the things I can do is I can show timing. So if I want to run one of these, you can see that these transactions are completing in 43 milliseconds, 65 in that case, 28 in that case. So this is milliseconds. This is basically instantaneous from a user perspective. Obviously, it's a local test network on the internet. You've got a bit more delay because of transaction latency. So you might get into a few hundred milliseconds, but certainly it's near instantaneous, the transaction completion. And if I click on this full results thing, then I can actually see the result that comes back from the peer. So if we jump back to this, the result record that comes back, that's precisely this. So this one had an ID of 29. The result of the computation was 3. There was no error in this case. That's good to know. I got 1100 convex copper in fees. That's the transaction hash. That's the hash that uniquely identifies the transaction that I sent in. How much juice did that use? And the lock is the position. So it's at block 12, position, transaction index 0. So that's all the information I need to go and look up the thing later if I want to, and just do my audits, do my analytics and stuff like that. So that's the result record that's coming back from the peer to the client. So it's a nice little tool. Yeah, you can actually see this stuff almost live happening. And on that other window, where's it gone? Here. You see the green dots. The green dots are basically the peers confirming consensus each time the transaction happens. As you can see, it's sort of pretty instantaneously, but that's these are confirmed blocks of transactions basically in the global transaction ordering. And all of those peers have the same copy of the state. Yeah, so all of these peers know that. If I connect to this one. So these are different peers, but if I say, okay, what is there's account 12, I defined it, so I can do 12 foo Peter. Says hello Peter. Yeah, I can see the function that was defined on a completely different peer, but they're all sharing the same global state, so they've all got access to the same code. They've all got the access to the same global state and the same execution capabilities. Okay, that's a quick demo. So in the execution state, is transaction synonymous with belief? Not quite. A belief contains transactions. A belief is a way of communicating transactions around the network between the peers. So users don't actually care about beliefs. The only people who care about beliefs are the peers, because that's how they reach consensus, by sharing beliefs among each other. But the belief contains the transaction. Yeah, it's the way that the peers communicate. Many transactions. A belief can contain many transactions. Yeah, so the beliefs contain a lot of transactions, and that's how the transactions get around the network. So every peer gets to see them, and then of course all the peers in convergent proof of stake are confirming that yes, we agree that these are all the transactions that we've got, and this is the order in which they should be executed. So I think of belief as like a transaction container that is useful for the network to achieve consensus. And it helps transmit that information around the network, but it is not the same as a transaction. It's a sort of different kind of message. This is all defined in the sort of the protocol. Yeah, so this is how convergent proof of stake works and how it achieves consensus. Good question. So I think as a transaction really as a single instruction, or actually this is a really important point. A transaction is an atomic instruction made to the computer, to the CVM, to our internet computer. By atomic, I mean either it succeeds fully or it fails and gets rolled back. And this is really important because if something fails, you don't want that to mess up the state. You don't want anything to go wrong. Yeah, you don't want a half-completed transaction. So a transaction doesn't mean just doing one thing. It can actually do many things. A transaction can define some code, it can create new accounts, it can deploy a smart contract, it can send some tokens, it can mint a new NFT. You can do all of that in a single transaction. Yeah, and so transactions can be pretty complex. They can be pretty big. You can put as much stuff as you want inside a single transaction. But if any one of those things fails, and then the entire thing gets rolled back. Yeah, and you get back to the original state that you had at the beginning of the transaction. And that's important when you're doing economic transactions, because if you want to receive some tokens and then send some different tokens in return, like as a swap, you don't want to be the person sending the tokens and then you don't get the other stuff back in return. Yeah, you want to make sure that either everything gets completed or the whole thing gets rolled back. So transactions enable you to do that. They enable you to do these atomic updates and to make sure that everything happens reliably. But what you put in that transaction, and they can be transactions with multiple different instructions, that's totally fine. That's up to you. It is actually also possible in Convex for transactions to contain other transactions. So you could have like a master level transaction and a whole bunch of sub transactions within it. Yeah. So that's actually quite useful in some cases. Like you might want to run a sequence of transactions and then bail out if one of them fails, but you still want to keep the results of the earlier transactions. Yeah, so you want things to happen sequentially, and you don't want the later transaction to happen if an earlier one fails, but you still want the earlier ones to happen. Then you can put multiple transactions inside a sort of what you call a multi-transaction that lets you specify slightly more sophisticated logic about what happens. And multi-transactions are useful if you've got some kind of maybe some trading system. You want to have a bunch of trades that get executed in sequence. There's a bunch of things you can do with it. But yeah, so that you can put transactions inside transactions is what I'm saying, which is sometimes pretty useful for more sophisticated use cases. What about creating and reading NFTs? Well, that's just a transaction. Yeah, so a transaction could say mint an NFT. That's perfectly valid transaction, because an NFT really ultimately is just what is it? I'm going to probably get this wrong, but import asset.nft.simple asset convex dot asset as asset I'm trying to remember the syntax to create an NFT with this tool. Yeah, that's it. So that's creating an NFT. Sorry, I couldn't remember quite the syntax for that one. But yeah, so these are different IDs for NFTs I'm just creating. So each of those is a transaction where I'm calling an actor. That actor is responsible for creating and allocating new NFTs, and I'm just calling the create function in that. So yeah, just a transaction or linking to it. Etch database, that is an entirely different conversation. I'll try and answer it quickly. The Etch database is the storage subsystem that Convex uses for storing all the data that Convex peers or other systems that use Convex core technology need. So all of the data structures, all of the tables, all of the indexes, all of the storage of different assets, the definition of assets, the code, everything in Convex. Big data structures that need to be stored, so you store them on disk. The Etch database is really our storage subsystem that stores all of that. Users do not need to know about Etch, and in fact they can't see Etch. They don't know it's happening. So the protocol in Convex merely says that peers need to update the global state in this way. It doesn't say anything about how they store the global state. Yeah, the Convex protocol actually defines what the computer behaves as. You know, so I do plus 1, 2, run a computation. It doesn't say anything about how the result of that gets stored within the peer. Yeah. And the Etch database is what we use to do that. It's a very, very efficient, specialized database designed for storing sort of compressed Merkle tree data, which is one of the reasons Convex is so fast, is because we've got this very efficient database. But it's completely invisible to the user. You don't know it's there. It's storing things on the peers. It's using it to store the global states and the different updates, and indeed the beliefs. The beliefs get stored on Etch as well. But users don't need to know about it. So it's more of a underlying infrastructure piece of the puzzle. The things that users can see is they can see some encodings. So if I could do encoding of 3, you'll see this OX1103. So that's like a blob with 2 bytes. That's the binary encoding of the number 3. Yeah, the first bit says this is an integer with 1 byte length, and this is the 3 part of it. So any data in Convex has an encoding, and that encoding is what gets stored on Etch. So users can see the encodings, but they can't know whether it's when and where it's stored on Etch, because that's really the peer's responsibility to manage all of that. Part of the peer's infrastructure, I would say. Although Etch is a very interesting topic, and we can definitely do another call and talk a bit more about Etch if that's something of interest. Okay, well I think that sort of brings us to the end of our time. But thanks for all the great questions. And I think it's really good that we sort of talk through some of the big ideas of computation, of what it means to be building a new kind of internet computer, and a bit about what we can do with it and how it all fits together. So thanks for the great questions. Thanks all for joining, and look forward to seeing you all next week. Take care. Bye for now.